Hi, welcome back to my series on group theory and physics. This will be the third lesson on permutation groups. And which is also known as the symmetric group. Sn. Usual notation. So if we have n objects, the permutation group will permute those n objects. There'll be a total of the order of Sn is n factorial. Now, last time we finished with a discussion of a order 6 group, just to review, and we called it D3 for the dihedral group on 3 elements. It's actually a dihedral group on equilateral triangle. And we also called it as S3, which is the permutation group on 3 elements. This is the last isomorphism between D3 and, Dn has 2n elements. Sn has n factorial elements, so they'll never be the same groups again. So let me just briefly review what we did. We have an equilateral triangle. We look at the symmetries of the equilateral triangle, and we can rotate by 120 degrees, 240 degrees, or do nothing. That's 3 elements. Or we can reflect about the medians of the group. Medians, perpendicular, bisectors, they're all the same thing for an equilateral triangle. So we have, if we label our vertices 1, 2, 3, we have 6 group elements for this symmetry group, where 1, 2, 3 goes to 1, 2, 3. That's where we do nothing. Then we have R 120 degrees. We'll always talk about counterclockwise rotations. So that would mean where 1, oops, I don't know what happened there. 1, 2, 3 would go to 2, 3, 1. So 1 would go to 2. This would go to 2. 2 would go, for R120, 2 would go to 3, and 3 would go to 1. So that is our rotation by 120 degrees. A 240 degree rotation would be where 1, 2, 3 goes to 3, 1, 2. We go 2 steps at once instead of 1 step. And then we have the reflections, and I'm going to denote them by a small r, and I'm going to subscript them by the point that they reflect through on this diagram here. So R1 is the reflection about this axis. We have R1, 1, 2, 3 goes to, and when we reflect about an axis, the point which labels that axis always stays the same. So R1, 2 goes to 1, 3, 2. The reflection about the axis going through point 2 is 1, 2, 3 goes to 3, 1, 2. And the reflection about the axis going through point 3 is 1, 2, 3 goes to 2, 1, 3. So these are basically, as you can see, 6 permutations. And we have the group S3. Now, normally when we discuss permutations, we start, if you look at any abstract algebra book or any math book or even the physics books, they usually start by doing it this way. You have like, one, for instance, those, you have like 1, 2, 3. These are the numbers you start, and then they each go to the number below them. And there's some advantage to this notation. I'll give an even better notation soon. Now, in theory, the numbers on top don't have to be ordered 1 to n. You could make it, a different ordering and then give the elements below which they go to. But then it's harder to understand the permutation. So this is sort of like the standard order. But I'll show you in a second why. Now, so this is one way of doing notation. And if we had like a 6, if we had an element of, let's say, an element of x6, we might have something like 1, 2, 3, 4, 5, 6 goes to 3, 1, 2, 4, 6, 5. So that's how we would describe an element. But we actually want to use what we call disjoint cycle notation. And you can easily show that every permutation let's call it permutation P is a product of disjoint cycles. Now, I'm not going to prove that to you, but just working out this example here, basically what you do is you take the first integer 1, you say where does it go? Well, we already said it goes to the one below it, so 1 goes to 3. Where does 3 go? 3 goes to 2. Where does 2 go? 2 goes to 1. So we already have 1 here, so when you come to the end of the cycle, you go back to the front. So then you go to the next integer that's not in here, and that would be 4. Where does 4 go? Well, 4 goes to itself, and that's it. 4 goes to 4, so that's a 1 cycle. And then the next integer that we haven't covered is 5. 5 goes to 6, and 6 goes to 5. So this is cycle notation, and in cycle notation, when you do like a cyclic permutation, this is equal to, we can sort of, it doesn't matter what order these numbers are in as long as they maintain the same order. So this is equal to 2, 1, 3, and this is equal to 3, 2, 1. So this is all the same thing. It doesn't matter, it's just which goes to which. But it's not equal to 2, 3, 1. You can't go backwards. That changes it. That actually makes it the inverse permutation. Let's just verify that, by the way, that statement that I made. So let's say we had to multiply 1, 3, 2 times 2, 3, 1. Now I haven't given exactly how to multiply permutations, but you always act on something to the right, and you go this way. One book I know, Ramon, which is a reference that I really like on his Group Theory of Physicists survey, he goes this way for a second, the opposite way. So, but this is the standard approach. It's function composition. You apply this to the object. Let's call this object. And then you apply this to the resulting object. So here, you would get that 1 goes to 2. Let's see how this product works out. 1, it goes to 2 on this cycle, and then the next cycle operates it on it, and 2 goes to 1. So 1 goes to 1, or that's a 1 cycle. Now let's look at what 2 goes to. 2 goes to 3, but then 3 goes to 2. So that's just a 1 cycle of 2 going to 2. And then again, as you can see, 3 goes to 1, 1 goes to 3. So and this is the identity permutation. So that shows you that to reverse a cycle, to find the inverse of a cycle, you just put it in the opposite order. Another way to get inverses of permutations, let's say I wanted the inverse of this permutation. Well, the easiest way, let's say you're doing some programming or something, just switch the top row with the bottom row. 3, 1, 2, 4, 6, 5, 1, 2, 3, 4, 5, 6. Now, this is the permutation. 3 goes to 1, and 1 goes to 2, and so on. But it's not in the standard order. If you reorder the columns, then you'll get the inverse of this. And the inverse of this is, of course, just each of these cycles, the same cycles, taking in the opposite order. Okay, so that's just some notation. I'll do some more notation. A transposition is a 2 cycle. So, 1, 2 is equal to 2, 1. This is a transposition. Now it's easy to show. Again, I'm not going to prove any of these things because they're so easy, but every permutation can be written as a product of not necessarily disjoint transpositions. And as part of the proof, you can do it by induction and various other ways, but let's just show that a 3 cycle, 1, 2, 3, how would we write that? Well, I'm just going to show you the answer, 1, 3, 1, 2. Now let's verify this. On the left, 1 goes to 2. On the right, 1 goes to 2. 2 doesn't occur in this cycle, so that's it. So it's 1 goes to 2, that's right. 2 goes to 3. Here, 2 goes to 1, and then 1 goes to 3. So again, 2 goes to 3. And 3 goes to 1. So here we have 3 is unaffected by this cycle, and 3 goes to 1. So here we've written this cycle as a product of 2 transpositions. And a cycle of length n, like, can be written as a product of an even number of transpositions of, let's call them 2 cycles. So a permutation is called even if it can be written with an even number and likewise it's odd. Everything is the same, except this goes to odd. So this permutation is even. It's a product of two transpositions. And in Sn, there are, in any permutation group, there are an even number, there are an equal number of even and odd permutations. And I think I mentioned this last time, but I'll mention it again. The even permutations form a group of order n factorial over 2, which we call and these turn out to be very important groups. A5 is the smallest simple. And simple is a technical term, group. I'll define it later, but basically it means that it has no invariant subgroups. So it has subgroups, but it doesn't have any invariant ones. And some of you may know that to factor a group, the factor theorem says that you have to factor by a what's called an invariant subgroup. Sometimes in algebra books this is referred to as a normal subgroup. So A5 is the smallest simple group. Now, I also, before I get too far, I want to mention Cayley's theorem. Again, I won't prove it. It's not hard. This is done in the beginning of every book discussing these kinds of things. I should have mentioned it earlier because why are permutation groups so important? Why do we care? Well, it turns out that every group of order n is finite, is I don't know why that happens sometimes, is isomorphic to a subgroup of Sn. So basically, if we study Sn, the permutation group, on n objects and all its subgroups for every n, then basically we've studied all groups. Now, that's not how groups are usually studied because it's not easy to do it that way, but something to know that in theory we just have to be experts on the symmetric groups for all n, and then we know everything about finite groups. I'll put finite here, even though when I say n, obviously it's finite. Now, okay, so I want to describe the cycle structure of permutations. So, consider a permutation of Sn which has alpha 1 cycles, alpha 2 cycles, and alpha k cycles. Now, each cycle has, like a 1 cycle has 1 element, a 2 cycle has 2 elements. So we have to get a total of n elements because we're a permutation of Sn. So the relationship is very simple, that n is equal to the sum from j equal 1 to k of j alpha j. In other words, the 1 cycles have 1 element, and we have alpha 1 of them, so that takes care of that many integers. The 2 cycles, when j is 2, we have 2 elements, and then we have alpha j of those, and so on. So that has to cover all integers n. So the question is, how many permutations of this structure? Well, what we have is we have a cycle. Let's call it a k cycle. Another k cycle. We have alpha k of these. And then we have k minus 1 cycle. And we have alpha k minus 1 of these. And we go all the way down to where we have our, 1 cycles. And we have alpha 1 of these. Now, basically, the question is, when we take our integers from 1 to n, how can we throw them in these? We know there's n factorial ways of like organizing the n integers, but there's some repetitions and redundancies. So let's find the redundancies. Well, first, since we have alpha k cycles, I could switch this one with this one and this one with this one. When I'm throwing in the integers, it's the same permutation. So that gives a alpha k redundancy. I don't think I spelled that right. Of for the cycles, I'm sorry, alpha k factorial. This alpha k factorial ways we can reorder these, and alpha k minus 1 factorial ways we can reorder these. And then within each cycle, within a k cycle, within a k cycle, let's say the integer 5 goes in here, I can place it here, I could place it here, I could place it here, or I could place it here. So we get j, because now I'm confusing myself. J or k. Let's call this a j cycle. We get j to the alpha j repetitions. So there's j possibilities here. Let's say, well, there's k possibilities here, but there's also k possibilities here and k possibilities here. So we're going to end up getting k to the alpha k, or I'm calling it here j to the alpha j. So whether you follow this argument or not, and think carefully, I think you'll see it makes sense, but it always confused me. The number of permutations is given by this formula. N factorial divided by the product from j equal 1 to k, j to the alpha j factorial. So let's illustrate this. with S4. So we could have alpha 1 equal 4, which meaning we have 4 1 cycles. Then alpha 2 equals 0, because we have to have, remember, 4 is equal to the sum of j alpha j. So if I put alpha 1 equal 4, 1 times 4 is 4, that uses up all the elements. All the other ones have to be 0. And the formula gives, when you work through it, 1 to the 4, 4 factorial, times 2 to the 0, 0 factorial, 3 to the 0, 0 factorial, 4 to the 0, 0 factorial, and this is 1. And the permutation, there's only one permutation with 4 1 cycles. That's the identity permutation, which is just this. By the way, when we use cycle notation, oftentimes we leave out the 1 cycles. So if we have a permutation like 1, 2, let's say in S4, 3, 4, oftentimes we'll just write it as 1, 2. Any of the integers that are not appearing, we just assume they're 1 cycles. Okay, just an aside there. So let's do our next thing. Let's say we have alpha 1 equal 2. So this takes away 2 elements. So now we have 2 elements left. There's only one place they can go. That's in a transposition. Alpha 2 equal 1, alpha 3 equals 0, and alpha 4 equals 0. And if you evaluate that formula, I'll do this for the last time, writing out explicitly the formula. We got 1 to the 2, 2 factorial, 2 to the 1, 1 factorial, 3 to the 0, 0 factorial, 4 to the 0, 0 factorial. This is equal to 6. So it says there's 6 permutations with this structure, and I'll write them out. 1, 2, 3, 4. 2 1 cycles, 1 2 cycle. Oops. So that corresponds to that. 1 3, 2 4, 1 4, 2 3, 2 3, 1 4, 2 4, 1 3, and 3 4, 1 2. So these are 6 permutations. They correspond to that. The next one would be alpha 1 equals 1, alpha 2 equals 0, alpha 3 equals 1, alpha 4 equals 0. The formula will give us 8, and these would be like 1 1 cycle and 1 3 cycle. So we'd have 1 2 3 4, 1 2 4 3, 2 1 3 4, 2 1 4 3, 3 1 4 2, 3. I'm sorry, I didn't do that in the right order, but 1 2 4, 4 1 2 3, and 4 1 3 2. And again, 1 2 3 4 5 6 7 8. So that's good. Our formula is working. Our next one would be alpha 1 equals 0, alpha 2 equal 2, alpha 3 equals 0, and alpha 4 equals 0. And our formula would give us 3. And here we have just 2 permutations, and we can have 1 2 3 4, 1 3 2 4, 1 4 2 3. These are 3. You might think, well, why can't we have 2 3 1 2? And you'll see that that's the same as this. I'm sorry. 2, 3, 1, 4, let's say. And that's just the same as this, because order doesn't matter when we write down discrete cycles. So there's only 3. The next one is, and I think this is the final one, alpha 1 equals 0, alpha 2 equals 0, alpha 3 equals 0, alpha 4 equals 1. We end up getting 6. This is 6 4 cycles. This is 1 4 cycle. You can check that these are all different. It should be obvious how I'm enumerating them. And so again, we get 1, 2, 3, 4, 5, 6. Very good. So altogether, you might notice we seem to have 5 types of permutations. 1, 2, we got 1, 6, 8, 3, and 6. Let's first check out. We should have 24 permutations. So I get 1 plus 6 plus 8 plus 3 plus 6. 14, 17, 24. So that's good, because 4 factorial equals 24. Now, notice each one of these corresponds to a partition of 4. So you can write 4 equals 1 plus 1 plus 1 plus 1 is equal to 1 plus 1 plus 2 is equal to 1 plus 3 is equal to 2 plus 2 is equal to 4. So these are the five partitions. Of the number 4 of 4. And so in general, each one of these things, you might notice that each of these permutations that are in the same one are sort of like the same. So we call this a class. I'll give a more formal definition of class in the next lesson or two, but this corresponds to a class. So for the permutation group, the number of classes is equal to the number of partitions of n. Furthermore, for any group, very importantly, as I'll show later, the number of irreducible representations of a finite group is equal to the number of classes. So I haven't defined any of this stuff. It's just something that I'm going to do. But keep in mind, for like here, for S4, we've shown that there are 5 partitions of 4. And then we seem to get 5 different kinds of permutations with different cycle structure. 2 permutations with the same cycle structure are in the same class. So we get 5 classes. That means that there's 5 irreducible representations of the group S4. That's important, as we'll see. Okay. So I want to finish here with a first look at Young diagrams. Now, the idea of Young diagrams is sort of to use a graphical way. Physicists love this, most physicists. Anthony Z doesn't love it, but it's a graphical way of figuring out representations and symmetries. And it's easier than substituting in these complex formulas, like this formula above, over here. Yeah, it's a reasonably complex formula, and you can get even more complex as you go on. So the idea is to use diagrams. So let me just define things. A Young diagram corresponds to, we have a partition of integers. Lambda 1 is greater than or equal to lambda 2, greater than or equal to dot 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 lambda n. We define alpha k as before, number of cycles of order k. And then now I define my lambda. Lambda 1 is the sum from 1 to k of alpha k. Lambda 2 is the sum from 2. You know what? This goes to n actually. 2 to n of alpha 2, and then lambda n is equal to alpha n. So for S4, let's start out. We had alpha 1 equals 4, alpha 2 equals 0, alpha 3 equals 0, alpha 4 equals 0. This implies lambda 1 is the sum of all of them, which is equal to 4. Lambda 2 is equal to, from here on up, we get 0. Lambda 3 equals 0, and lambda 4 equals 0. Now, the Young diagram, I didn't say this, I should have mentioned it, corresponds to, first you put lambda 1 boxes in the first row. So this is that. And then below it, you put lambda 2. Remember, lambda 1's, you're never going to have something that goes like this, because lambda 1 is greater than lambda 2 is greater than lambda n. So we won't ever have that. But so this corresponds to the 1 cycle, to the identity. This is an example. It's only 1. And now we have like alpha 1 equal 2, alpha 2 equal 1, alpha 3 equals 0, alpha 4 equals 0. So now I get lambda 1 equals 3, lambda 2 equals 1, lambda 3 equals 0, lambda 4 is equal to 0. And so now our Young diagram corresponds to 3 boxes on top. And then we have 2 boxes below that. And 1 box below that. I'm not doing this right. Lambda 1 is 3. Lambda 2 is 1. No, we have no more boxes. And it's only 1. So this is the box that corresponds to a permutation which has a structure of 1, 2, 3, 4. Now let's keep going. We have alpha 1 equals 1, alpha 2 equals 0, alpha 3 equals 1, alpha 4 equals 0. This means lambda 1 equal 2, lambda 2 equal 1, Remember, it's the sum from everything onwards. Lambda 3 equals 1 and lambda 4 equals 0. So this diagram is 2 boxes, and then 1 box, and then 1 box. And these two diagrams here, these are called conjugate diagrams. If you flip them over, you can see how one becomes the other one. And the permutation, the sample permutation that this corresponds to would be this. Now, what you do with these things, there are various things you do with these diagrams, but sometimes you put numbers in them, and then you get young operators, like symmetry operators, even and odd operators. We'll do that at a future time, but I just want to just show you, in case you've ever seen these diagrams, at least a little bit of. So this one is alpha 1 equals 0, alpha 2 equals 2, alpha 3 equals 0, alpha 4 equals 0, lambda 1 equals 2, lambda 2 equals 2, lambda 3 equals 0, and lambda 4 equals 0. And so this corresponds to a diagram like this, and this is called a self-conjugate diagram. And then finally, I have alpha 1 equals 0, alpha 2 equals 0, alpha 3 equals 0, alpha 4 equals 1, a basic permutation. Any 4 cycle. Now we have lambda 1 equal 1, lambda 2 equal 1, lambda 3 equal 1, lambda 4 equal 1. And so this is just 4 1 boxes. Now, again, you might ask, what's the use of this, and so on, but when you multiply representations in physics, particle physics, and everything, you'll end up using these diagrams. There's also things like hook and ladder formulas for determining dimensions, and you can use them for like SU2 groups and SU3 groups. A typical hook and ladder formula is something like this. Say we have this. What you do is for each box, you go like that, to the right and down, and you ask how many boxes you intersect. So this one is 3, and this is 4. Here I intersect, there's nothing on the downside, and there's nothing on the downside. So here this is 2, and this is 1, and this is 1. So the hook and ladder would be just the product of those things, would be 4 times 2 times 1 times 1, which is 8. So this tells me there's 8, that there is an 8-dimensional representation. No, I'm sorry. So now you take n factorial over the hook and ladder. Let's call it h. So you take 4 factorial over 8, which is 24 over 8, which is equal to 3. So there's a 3-dimensional representation just want to see one thing. So here, how many cycles did we have for that 1 1 1 1 2 3? This we had six cycles, 6 permutations. But anyway, this sort of tells me, if I remember correctly, that this graph, this Young's diagram, corresponds to a 3-dimensional representation of the symmetric group. And there's ways you put in, like for SU2, you put in integers 1, 2, and then you multiply those integers and so on. we'll get back to that later. So I'll see you next time. Thank you for watching. And next time we'll start going into some more group properties, and I'll have to talk about representations and irreducible representations before I can start applying it to some physical problems. Thank you very much.